Okay, let me go ahead and get started with this homework 7 review. We need to explain hybridization of a carbon. So the issue with this that Linus Pauling was trying to solve was the fact that the electron configuration and the energy level diagram for carbon looks like, whoa, wrong color, 1s, 2s, 2p, one up, one down, one up, one down, one up, one up. There's only 6 electrons for carbon. So the issue is a covalent bond is an electron from one atom being shared with an electron from another atom. And we can't share when they're paired up like this because the orbital's filled. So what I need is another electron from another substance coming in here. And maybe the substance can actually bring 2 electrons with it and fill that last spot. So what it looked like is that carbon can only make 3 bonds at most, but we knew it made 4 bonds. So what Pauling said was the energy difference between the 2s and the 2p is practically insignificant, and so he redrew the energy level diagram for carbon as 1s, and then he said 2sp3. So this 1, 2, 3, 4. So you're going to see we still have 6 electrons, and now I've got 4 locations that the electron can be shared. So somebody could come in, another substance could put an electron there, and there, and there, and there, and now I've got 4 bonds, 4 single bonds. This is called sp3 because technically there's 1 s orbital and 3 p orbitals. After Pauling had this thought, he verified, because he knew what the shape was from X-ray crystallography, he had Heisenberg do calculations for it, and then what you end up having is, he asked, what would happen if I took an s orbital and I added it to a py, a pz, and a px orbital, mathematically, adding these shapes together. And in the end, what you end up with is exactly what they see in X-ray crystallography, which is a tetrahedral shape. So it was verified mathematically as well as experimentally. Let's look up the model 3-hexene, draw it here. All right, so 3-hexene is carbon, 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 carbon. 6 carbons because it's a hex. And ene means a double bond at carbon number 3 going to 4. And that's the molecule. So I'm going to throw up hydrogens around this. So there's my Lewis structure. No lone pairs of electrons, and my Lewis structure is wrong, sorry. These are not here. What I have are 4 bonds around every single carbon. Carbon number 1, carbon number 2, carbon number 5, and carbon number 6 are all sp3 hybridized, and they all have a tetrahedral molecular shape because they're connected to 4 different objects. In this case, that line, sorry, I should have said something about that. A line with nothing on it means a hydrogen. I'm just being lazy. But carbons number 3 and number 4, they're only connected to 3 different things. So carbon number 3 is connected to that hydrogen, that carbon, and that carbon twice. And the same kind of situation happens with carbon number 4. So what we have here is sp2, and this is trigonal planar. This would provide a kink or so in the middle of this 6 carbon chain molecule. So the question is, how many sigma and how many pi bonds are here in this molecule, and what are the shapes around each carbon? So anytime there's any S characteristic, that's a sigma bond. So, and anytime there's a double bond, that's just P by itself. So I've only got 1 pi bond. So let's change colors here again to, I don't know, black. So here, this double bond here is my 1 pi bond, and every single other bond, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is that 16? Did I miss anything? Looks like 16. Those are all sigma bonds. So I've got 16 sigma bonds, and I've got 1 pi bond. If I missed one, sorry about that. I think I got them all. Okay. I kind of cheated for the last one here. I went and found myself a little picture and inserted it for molecular orbital diagram for nitrogen. We don't really care about the 1s section because there's going to be 2 there. We've already passed the noble gas. So what we're concerned about, nitrogen's 1s, 2s2, 2p3. So we don't care about those 2 electrons in the nitrogens. So we're only going to care about these 2 and these 3 electrons. So I've got 2 here, and then I've got 1, 2, 3. And then I got 2 here for my other nitrogen, and 1, 2, 3. Okay, so we just go ahead and fill in. Put 1 down here and 1 here. And then up there and then up there. So ding ding, and then you go down there, and you go down there, and then you go there, and you go there, and then you go there, and then you go there. And so what we have here are, for red, I'll circle the anti-bonding. The only anti-bonding electrons we have are these because of this little star thing right here. And then the rest of these, I'll put those in green. Those are the bonding electrons. And so I've got 2, 4, 6, 8 bonding electrons. So the equation for the number of bonds is 1/2 of the bonding electrons, in this case 8, minus the anti-bonding electrons, in this case is 2. And so we end up with 3. So nitrogen should make 3 bonds. And nitrogen does make 3 bonds when it's N2. That's the Lewis structure. Thanks.